have just completed the question number 10. Let us take up problem 11. I read out the question. In the circuit shown, P is not equal to R. The reading of galvanometer is same with switch S open or closed. That means whether the switch is open, that is the circuit is open circuit like in that particular branch, or it is closed. Whatever be the case, then he is asking you to identify the right option there. What are the four options given? Current across R is equal to current across G. IR is equal to IG. That is the first option. IP is equal to IG. That is the second option. IQ is equal to IG. That is the third option. IQ is equal to IR is the fourth option. You just have to identify the correct option out of the four. What is the circuit given? Let me first of all draw here. He is just giving you four resistances connected in the form of a Wheatstone bridge. Those four resistances are given as P, Q, R and G. So what is the way? Look at, this is one resistance, this is the second, this is the third, and here he has given a galvanometer like. That's what has been given. And of course across these two there is a tap key. That key is given this way. It's given as S. And of course he has given us these two ends are connected across a cell like this, which can provide a potential difference V like this. This is mentioned P, this is mentioned Q, and this one is mentioned as R. So this is the circuit given. First and foremost, what is the condition he has mentioned? You observe that one carefully. In the circuit shown, P is not equal to R. So P and R are not equal to each other. That is the condition what has been mentioned there. P and R are not equal. Fine. Reading of the galvanometer is same, whether the switch is open or closed. So one should directly understand, when the switch is open or closed, the reading of the galvanometer is same. That means one should understand that this particular construction is a well balanced Wheatstone bridge. I once again repeat, the moment he is expressing that the value of galvanometer current, that is the reading in the galvanometer, is same whether the switch is open or the switch is closed. Whether the switch is open or closed, if the galvanometer reading is same. What is the meaning of that? This particular construction is a perfect Wheatstone bridge, following every condition related to that Wheatstone bridge as such. And what is the condition in Wheatstone bridge? Balancing part of it, we know it. What is the condition? P and Q, they should have the same current. That means the current across P and current across Q must be the same. If at all this is a well balanced Wheatstone bridge, currents across these two resistances are going to be equal. Why are they equal? Because these two become in series now. Similarly, these two will carry the same amount of current. That means if I take this one as IR and this one as IG. So what is the condition here? If the bridge is balanced, If the bridge is balanced, then what can we understand? Then you can write P and Q are in series. This implies current across P and current across Q are supposed to be equal. And exactly in the same manner, and I can write R and G are in series. Even these two also will be in series. That implies current across R and current across G are also going to be equal. So only thing you should understand here is these two are the conditions which are supposed to be valid for this particular circuit. When they are valid, our answer must be either this or this, or both also sometimes. Now look at all the four options given carefully. First option says IR is equal to IG. That of course is true, one. And second option you see, IP is equal to IG. IP is not equal to IG. Officially IP must be equal to IQ. So second option is not correct. Come to the third option what has been provided. IQ is equal to IG. That's what has been given. IQ is equal to IG. This is also not true because IQ must be equal to IP, not IG. So the third option is also not correct. Then what is the last one you see? IQ is equal to IR. That has been given like this. That also is not correct. So what must be the correct option for you? IR must be equal to IG. That is the very first option given in this particular question. So you can say now the answer for this question is simply the first option, that is A. But all of you should immediately get to your mind that this is a Wheatstone bridge and very well balanced Wheatstone bridge. How do we know that it is well balanced one? He is very clearly giving you a clue there that whether this particular switch is on or off, in both the cases galvanometer reading is the same. That wording itself makes you understand that this is a very well balanced Wheatstone bridge. So correct option for this problem number 11 is going to be A. That is the first question in this order, of course 11th one. So that is the one what we have to remember. Look at the next problem given in the same order. The effective resistance between the points P and Q of the electrical circuit shown in the figure is how much? Effective resistance he is asking. That means one should first of all have the basic concepts of resistances connected in series and even in parallel. So let me first of all complete the reading part of the question. Find the effective resistance between the points P and Q of the electrical circuit shown in the figure. What is the circuit given? You see first. He has just given you three separate branches like. What are the values given? You see. One is a resistance 2R here, another resistance like this, one more resistance this way, one more in this fashion, one more pair like this. He has taken them up like this. One resistance is across this, one more resistance is across this. That is what has been provided to us in the problem. This is given to R, this is given to R, this is R, this is R, this again is given to R, this again is given to R. And of course he has mentioned here this value is to R, this value is to R, this one is P and this one is the point Q. Across these 2 points we just have to calculate what is the effective resistance of the circuit as such. But try to understand one point before taking up this. We once should know what exactly the concept of resistances connected in series. What exactly the concept of resistances connected in parallel. So one should understand directly when we consider series circuit of resistances. R series will be R1 plus R2 plus R3 and so on and so forth. Resistances are going to be added up when they are all connected directly in series as such. That is one area one has to remember. Exactly in the same manner, when resistances are connected in parallel by any chance, then the reciprocals of their individual resistances are to be added up to get the reciprocal value of the effective resistance. So 1 by R parallel, that is equal to 1 by R1 plus 1 by R2 and so on and so forth. But here, if you just look at this circuit carefully, this total circuit is now resembling the part of Wheatstone bridge like. So what you find in this part, you see, in this particular portion, this 2R does not carry any current. Exactly in the same manner, in this particular portion, this 2R also does not carry any current. What is the reason behind? If you just look at this particular point and this particular point, these 2 points will have the same potential. If I take this point as A, this point as B, this point as C, this AB and this BC, they will be having the same potential. When potential is same, what is the meaning of it? There is no potential difference across the system. When we are finding the potential difference between the points to be 0, then one can understand no current that flows across. So what do you find in this particular circuit now? Across 2R resistance and across this resistance of 2R, no current that flows across. Remember this point thoroughly. The moment these two are becoming dummy resistances. Why I am using the word dummy? You can understand a resistance without carrying a current in that circuit is of no use for us. Unless until there is some current that is flowing across, we will never entertain that resistance anymore. So what we should understand from this, these two resistances need not be considered now. The moment you eliminate these two, how this total circuit now becomes, look at that. You will be finding two resistances like this, two more resistances like this, two more resistances like this. So totally 3 pairs of resistances are now connected in parallel, and across that we are having a cell of potential difference V. So what is it you are finding here? This now becomes 2R, this now becomes 2R, this is R, this is R, this again is 2R, this again is 2R. So what you can predict from this? These two now are in series. When they are in series, their effective resistance becomes 4R, 2R plus 2R. Exactly like that, when these two are connected in series, the effective resistance now becomes 2 small r, R plus R, that now becomes 2R. Exactly in the same manner, this 2R and this 2R also in series, so effective value will now be 4R. So what you can now predict from this system, please? That is as well equivalent to 3 resistances connected in parallel this way. this is the point say Q, this is the point say P. Then what you can understand here, this is 4R, this is 2R, this is 4R. So what will be the effective resistance? 1 by R effective is 1 by 4R plus 1 by 2R plus 1 by 4R. What will be the value here? It is, this value can now be written as 2 by 4R plus 1 by 2R. This of course can be rewritten as 2 capital R small r in the numerator capital R plus small r. That is equivalent to effective resistance. Then what will be the value of effective resistance? It is reciprocal value. So reciprocate this one, 2RR by R plus R. That must be the correct option for this question. Now if you look at the 4 options given, what is the first option you see? 2RR by R plus R, first option. What is the second option given? 8R into R plus R, that is this, by 3R plus R, that is the second option. 2R plus 4R, that is the third option. 5R by 2 plus 2R, that is the fourth option. So obviously you can understand straight away that this is the correct option for it. This correct option means what will be the answer for this particular question now? The answer is A itself. The very first option, that is the correct option for this. That is actually this problem number 12 what we have. Simply speaking, a simple concept of resistances connected in series and in parallel. Only thing you should understand from this case is no current that flows across this resistance, no current that flows across this resistance. If you can identify that one, it's not at all a big problem, a very, very simple and easiest possible question as such. Let us switch over to problem number 13. Let me read out the question. A different model one. A moving coil galvanometer of resistance is used as an ammeter. Using a resistance 0.1 ohm, the maximum deflection current in the galvanometer is 100 microampere. Find the current in the circuit so that the ammeter shows maximum deflection. And options are given this way. First option is given 100.1 milliampere. Second option is given 1000.1 milliampere. Third option is given 10.01 milliampere. And fourth option is given 1.01 milliampere as such. That is the concept. So let us first of all take what is the data that has been provided to us. A moving coil galvanometer of resistance 100 ohm. G value is given 100 ohm for us. Is used as an ammeter using a resistance of 0.1 ohm there. That of course is called shunt. It is now 0.1 ohm over here. What next is given? Find the current in the circuit, right, so that the ammeter shows maximum deflection. We want the total current there. And what is the current that is passing through galvanometer? It is given 100 microampere. So current across the galvanometer is 100 microampere. First and foremost, I just want to remind you, how do you convert a galvanometer into an ammeter? In fact, every one of us we know, both ammeter and galvanometer used to measure current only. But what makes the difference? Difference is quite simple to understand. Galvanometer measures smaller values of currents with utmost accuracy, whereas ammeter is used to measure larger currents over there. The difference between these two is only that much. That means if you want to measure greater values of currents, larger currents, then we go for ammeter. When we just want to measure smallest values of current, smaller currents like in any circuit with the utmost accuracy part of it, then we take a galvanometer. But in true sense, galvanometer is the only instrument which was constructed in the beginning. What we are doing in this particular case, every one of you can understand. Galvanometer can be converted into an ammeter. Similarly, a galvanometer can be converted into a voltmeter also. Which galvanometer we prefer taking here? Generally we go for moving coil galvanometer. That moving coil galvanometer can be converted into an ammeter as well as a voltmeter. Once again, you people should understand the difference between these two. Ammeter measures current, whereas voltmeter measures potential difference between any 2 points in any circuit. So that is the difference between these two generally. Now come to the first part of it. How do we convert a galvanometer into an ammeter first? This question is purely based on that particular concept only. So let me just give you here, if you take a galvanometer and if you connect a shunt resistance in parallel, this particular combination or the total construction is now to be called as an ammeter. So what do you find in ammeter? A moving coil galvanometer is shunted with a very low resistance, then it will be converted into an ammeter. The criteria here is the resistance what is connected in parallel must be as small as possible. What is the meaning of it again? The smaller the value of S, the greater the value you can measure using that ammeter. If you want to measure using ammeter larger currents, then shunt whatever we are connecting there, the shunt resistance, that is supposed to be as small as possible. Small in the sense not in the size, in its magnitude. The resistance value should be very, very, very less. The lesser the resistance of S, the greater the range to whatever extent you can measure using that ammeter as such. If you take this one, if I consider the current that is entering into the circuit as I, after reaching here, a part Ig that goes across the galvanometer, a part Is that travels across the shunt. You people can straight away understand directly this way. Both will once again reunite here to give the total current as I. So this is actually the internal way of distribution of current in the system. In addition to that, what is this Ig? Ig stands for the current that is passing through galvanometer. What amount of current that is passing through the galvanometer, that is what we are taking it as Ig here. And this Ig has a formula which all of you know, G by S by G plus S into I, that is the formula. Observe carefully what is what out of it. S gives you the resistance connected in parallel. G gives you resistance of the galvanometer. I tells us the total current across the system. Exactly in the same manner, you can even write what is the part of current that is passing through the shunt. How much amount of current that is passing through shunt. That Is can be written as G by G plus S into I. This is the formula. So, whenever a moving coil galvanometer is converted into an ammeter, these are the two formulae which you people have to remember. Not only that, theoretically speaking, since these two resistances are connected in parallel, the potential difference across the galvanometer and across the shunt are going to be equal. So what is the common factor over here, you know? In ammeter, PD across G and PD across S are equal. Whereas in a voltmeter, currents are going to be equal across the galvanometer and across the resistance connected in series over there. So what you should remember for an ammeter over here is current across the galvanometer Ig is equal to S by G plus S into I. Similarly, Is is equal to G by G plus S into I. What is this Is now to be called? Is is nothing other than the current that is passing through that resistance which is shunted across the galvanometer. So, in this particular problem, this is the formula which is going to be hold good. So, what we people have to check, look at. We know now Ig is equal to S by G plus S into I. That is the formula I have brought. You can understand what is this value of Ig now. It is 100 microampere into 10 power minus 6 is equal to shunt is given 0.1. G plus S now becomes 100.1 into the value of I. And what is the question he is asking? You can easily guess. Find the current in the circuit so that the ammeter shows maximum deflection. So that means maximum current he is asking you to calculate. So what can we write now? This decimal and this decimal, you cancel them first. Then what can we write here? This can be written as I by 1001. Now come on, multiply. This implies I is equal to 100 into 10 power minus 6 into 1001. You can cut these two zeros 10 power minus 4 times. 10 power minus 4 if you multiply with, can't I write this one 100.1 milliampere please? In fact, I will be getting this one 100.1 into 10 power minus 3 ampere. But every one of us, we know very well 10 power minus 3 is to be called as milli. In that order, of course, we can all understand. Milli stands for 10 power minus 3. Micro is 10 power minus 6. Nano 10 power minus 9. Pico 10 power minus 12. Fermi 10 power minus 15. These particular conversions, every one of you should remember. In this case, it is 10 power minus 3 which is to be called milli. So what must be the current across the system now? 100.1 milliampere as such. So looking at the options given there, you can all understand first option is the correct option for us. First option given 100.1 milliampere. Second option given 1000.1 milliampere. Third option is 10.01 milliampere. and fourth option is given 1.01 milliampere. So you can directly understand the answer for this particular problem is the very first one, that is A only. That is the concept. So everybody should have the concept of ammeter and voltmeter, which we are going to get when galvanometer is connected across a resistance like. Ammeter means what is the condition? A very low value of resistance is connected in parallel to the galvanometer. If it is voltmeter, a very high value of resistance will now be connected in series to the galvanometer as such. So based on that concept of ammeter, this particular problem has been framed. That is problem number 13. Let us check problem number 14. A 4 microfarad capacitor and a resistance of 2.5 mega ohm, or even you can call it as milli ohm also, sorry, million ohm, are in series with 12 volt battery. Find the time after which the potential difference across the capacitor is 3 times the potential difference across the resistor. And of course he has given one value also, given log 2 to the base e, that is 0.693. What are the options provided to us? First option is 13.86 seconds. Second option is 6.93 seconds. Third option is 7 seconds. And fourth option is 14 seconds. In reality, first option is the correct option for us as far as this problem is concerned. But what is the problem given? Let us just draw a small circuit for that. A 4 microfarad capacitor and a resistance of 2.5 mega ohm are in series with 12 volt battery. That is the concept. Look at this one carefully first. I just take a capacitor, I just consider a resistance, both are now connected across a cell like this. You can understand well, both are in series. Very clearly it is mentioned in the problem as well. This is 4 microfarad and the other one is 2.5 mega ohm or million ohm. You people should understand whether you call it mega or million, it is a 10 to the power 6. Micro and mega are quite opposite terms, like we can remember almost. Micro is 10 power minus 6 and mega is 10 to the power plus 6. That is the major difference. So if you look at the voltage over here is given as 12 volt. This is the construction. What he is asking you to calculate, after what time the potential difference across the capacitor is 3 times the potential difference across the resistor. That means potential difference across the capacitor must be 3 times potential difference across the resistor. So if I write here, this is VC and this one is VR. This is across the resistor, this is PD across the capacitor, and the relation between these two is given like this. Then I can write VC is to VR is equal to 3:1. That is what has been mentioned. 3:1 means what? 3 parts for capacitor, 1 part for resistor. You can certainly understand in this particular case, then 3 parts means VC can be written as 3/4 of the total value V. That is actually the implication there you people have to remember. That in the sense, if you take VC is 3:1, that we can even write it like this also, 3/4 of V and 1/4 of V. That is the concept. What we should understand here, first and foremost, what is the background of this circuit? What is the background? This is RC circuit. In RC circuit, when there is growth like, we people all know there is a formula directly. What is that formula we are having? Vc must be V into 1 minus e power minus t by Cr. All of you should recollect this formula first of all. Vc, that is the potential difference across the capacitor. V, that is the total voltage applied across the system of RC circuit. E to the power minus t by Cr. What is this Cr here called? It is a tau. What is this tau called? It is called time constant. You people can understand this capacitive time constant, we call it. What is the formula for that? It is a Cr. You can understand this is the concept over there, capacitive time constant. So, if you take this Cr is represented by tau, this is the formula what one has to go for. If I just consider the values over here, when we write that equation over here, Vc is equal to V into 1 minus e power minus t by Cr. You can understand well when voltages are in the ratio 3:1. That's what has been given. Vc is equal to 3 Vr. So what we people can write here? The concept is quite simple. Look at this Vc. Vc in terms of V, let us write first. What will be the equation we are getting? This implies V into 1 minus e power minus t by Cr is equal to V over 4. Right. Which V over 4? 3V by 4. What is the reason? You can certainly understand here Vc is equal to 3 times Vr. That is actually the concept. Vc is to Vr is 3:1. 3/4 of the total value. So you can now cut this V here. Look to the next step. 1 minus e power minus t by Cr is 3 by 4. Look at the next step now. You can write e power minus t by Cr is 1 minus 3 by 4, which now becomes 1 by 4. But you people can understand mathematically, it can be rewritten this way. E to the power minus t by Cr is equal to 4. What for? E to the power t by Cr. I just write 1 by e to the power t by Cr is equal to 1 by 4. So e power t by Cr can be written as 4. Then what is the next step you can write over here? You can certainly understand that one. T by Cr is equal to log 4 to the base e. Log 4 to the base e can be rewritten 2 into log 2 to the base e. What for you can better guess? 4 can be written 2 square. Log m power n is n log m. So 2 times log 2 to the base e is equal to t by Cr. Then what is our calculation to be taken up here as? T is equal to how much? So t is equal to 2 Cr into log 2 to the base e. You can all understand twice. C value is given as 4 micro. R value is given as 2.5 mega ohm. log 2 to the base e, that is ln2, he gave 0.693. Now if you cut these two values, 4 times 2.5, it is going to be 10. So you can now write this one 6.93 into 2. So this becomes 6, here 8, here 13. 13.86 seconds will now be the time that is taken. So what you people should understand here, after what time, that's what he is asking you, find the time after which the potential difference across the capacitor is 3 times the potential difference across the resistor. So what you should understand out of this one now, you people can straight away take it for granted, this value of VC is to VR should be 3:1. After what time it becomes 3:1. That's what is the question. So you can identify directly this way. This as well can be rewritten like this also. VC is equal to 3/4 times the value of V also you can write. That only I have considered here. So what you should understand, this is actually the equation for CR circuit. In terms of the potential across the condenser, if you can remember that formula along with CR, which is called time constant over there, you directly can work out the value what is needed. So what is the correct option for this question number 14 now? It's 13.86 seconds. So the very first option is 13.86. Therefore, I just can take up the answer for this particular question is the very first option, A itself. But all of you should think that this particular point you might have already discussed in transient currents, growth and decay in CR circuit. That is a charge, of course. Growth and decay in LR circuit, that of course current. So those concepts will come into picture as far as this model question that is concerned. So this is problem number 14. Look at the next problem, that is problem number 15. This is a different model question. 2 bars of radii R and 2R are kept in contact as shown. An electric current is passed through the bars. Which one of the following is correct? He is just giving us 4 different options. Heat produced in bar BC is 4 times the heat produced in bar AB. That is the first option. That means you have to calculate heat energy that is generated across the first bar, across the second bar. Then you have to relate them. If this tallies with the first option, fine. Otherwise, the second option, electric field in both halves is equal. That is the second one. Third option given is current density across AB is double that of across BC. And fourth option given, potential difference across AB is 4 times that across BC. So let us first of all check, looking to the problem given, the figure given, which option out of the 4 that is going to be tallied as the answer for this. Let us check first of all the figure given over here. He said there is a bar like this, there is another bar like this. Very clearly it is mentioned in the question that this length is L by 2 and this length also is L by 2. So you certainly can understand, if I take the total length as L, each one is half L by 2, L by 2. Their lengths are equal, that's given very clearly there. If I take this one is the axis of it, this radius is given as r, this radius is given as 2r. That means radii of cross section are different. This is a bar. Bar means every one of you can understand it's like a cylinder. The radius of this portion of the bar is r. The radius of cross section of this portion of the bar is 2r. That's what has been given. And of course same current that is passing through the system like he has given. I is same. That is one aspect what has been given. Now first option you look at. Heat produced in bar BC is 4 times the heat produced in bar AB. Let us check that point first of all. Heat produced, in true sense, it is I square RT. For this, let me remind you 2 more cases. All of you should know well what is the formula for electric power. You all can recollect this formula. In fact, I am going to give you 3 chains of equations which are useful in solving such model problems. If I consider electric power, it can be written as voltage into current, potential difference into the current value. Applying Ohm's law, which is V is IR, I can write I square R. According to Ohm's law only, I can be written as V by R, therefore I can write V square by R. So all of you should understand straight away, electric power, whenever we want to calculate, either of the 3 equations we can use. Either directly V into I, or directly I square R can be taken, or V square by R can be considered. That is the concept. Suppose if I just want from this one, what is the amount of work done in passing current? What amount of work that has been done while passing the amount of current, or what is the work that has been done by the charges which are flowing across? Every one of you know W can be written as power into time. Why? Because power is rate of doing work. W by T is called power, so we can write work is equal to power into time. If you write this way, the equations once again can be repeated like this. VIT you can write, I square RT you can write, V square T by R you can write. So when you talk of power and when you want to know work, power into time gives you work done. But at the same time you can understand heat energy generated due to the current, whatever that is flowing across the system. How to just calculate heat energy over here? Heat energy can be written as W by J. All of you know this formula as Joule's law. W is equal to JH. H is equal to W by J, where J is called mechanical equivalent of heat. That has got another name also. It is also called Joule's constant. And of course we can all understand the value of J, that is going to be 4.186 joule per calorie. For all practical calculations, we write this one 4.2 joule per calorie. But at the same time, you people should understand, in SI units, work and heat energy are taken to be same, because the value of J is 1 in SI units. Since J is 1, in SI units, work done and heat energy generated both are going to have the same magnitude. So what you people should understand here, W and H you can calculate using the same set of equations. Now I am considering heat energy from this formula as such. What is that heat energy here? I square RT I am considering. Now the question is, when we have 4 equations here, why to go for this equation only? You people can straight away understand that. What is it? 2 rods are connected in series. In series, current remains constant. Therefore, I know I square is constant, time of course is constant, then I can directly write H is proportional to R. If I write H is proportional to R here, what is the resistance of the first rod? Let us take it. What is the resistance formula? Rho into L by area of cross section. In other words, I can write rho into L by area of cross section is pi RA square. But you people know pretty well L is same for both. Therefore, rho being constant, L being constant, pi being constant, what can I write now? Resistance is inversely proportional to square of the radius of cross section. So resistance is inversely proportional to square of the radius of cross section. What are the radii provided in the problem? Look at those two and finalize your result. So what can we write now? RA by RB is equal to RB square by RA square. So observe this point carefully. These capital letters, they are referring to the resistance values. Small letters, they are referring to the radii of cross section of both the rods. So what we should write now? RB is simply R. So R square by what is RA? 2R whole square, which is 4R square. That now becomes 1 by 4. The moment you are finding it as 1 by 4, come on, cross multiply this one please. RB will now be equal to 4 times RA. But you know pretty well R and H are directly proportional to each other. Therefore, what can we write? Heat energy generated in the second rod will now be equal to 4 times the heat energy generated in the first rod. So what is the very first option given you look at? Heat produced in bar BC is 4 times the heat produced in bar AB. Very clearly you are getting the same. Heat produced in the first bar, heat produced in the second bar, I have calculated and I have related them. So what is it you are getting? Heat produced in the second bar is equal to 4 times the heat produced in the first bar. So that itself is our answer. So what we should understand here now, the answer for this particular question is the very first option again. What is that first option given? I read out once again. Heat produced in bar BC is 4 times the heat produced in bar AB. So you can definitely understand this is the bar AB what he is talking and this is the bar BC what he is talking. So the heat generated in the second one is 4 times the heat generated in the first one as such. That is the relation what we have got. And for all those, these equations you people need to have in memory. So if you are thorough with these concepts, any problem that is coming or that is asked based on heating effect of current can be solved easily. So this is problem number 15 what we have. Let us check problem number 16. A resistance of 2 ohm is connected across one gap of a meter bridge. The length of the wire is given 100 centimeter. And an unknown resistance greater than 2 ohm is connected across the other gap. When these resistances are interchanged, the balance point shifts by 20 centimeter. Neglecting any corrections, the unknown resistance is how much? Of course, he has given 4 options. First option is 3 ohm. Second option is given 4 ohm. Third option is given 5 ohm. And fourth option is 6 ohm. And correct option here is no doubt the first one. That is 3 ohm we will get. How come? Let us first of all finalize. He is just talking about a meter bridge here. Let me just remind you in brief what is the principle on which this meter bridge works. Every one of you know it well. Meter bridge is a simplified form of Wheatstone bridge. I repeat, meter bridge is a simplified form of Wheatstone bridge. In Wheatstone bridge, to balance the bridge and to make the current across the galvanometer 0, you need to change 3 known resistances. 3 known resistance are to be varied so that to make the current across the galvanometer 0. Then only we can say the bridge is balanced. Then only we can apply the principle which is the balancing condition of Wheatstone bridge, which is P by Q is equal to R by S. But one thing you should understand here. Calculating the value of S, which is an unknown value out of the 4, by changing 3 resistances which are P, Q and R in a Wheatstone bridge is time-taking process. That is why we people have made it easy by constructing a meter bridge here. Just to recollect once again what you find in a meter bridge. You will be having 3 metal strips like this. 2 of them are L-shaped metallic strips and 1 is a straight metallic strip. All the 3 are directly mounted on a wooden base of length exactly 1 meter. Each metal strip you will be finding 3 connecting terminals. So you can find totally 9 connecting terminals overall. Across these 2 terminals, we just connect a uniform cross-sectional wire of exactly the length 1 meter. And you know well, across these 2, that is extreme ones I am talking, we connect a cell and a key like this. This is the cell what we people are giving, and this one is key what is connected. And all of you should understand straight away, this circuit is called primary circuit. What is the importance of a primary circuit either in a meter bridge or in a potentiometer like? Primary circuit is responsible for giving required potential difference to the system. That means what? In the primary circuit, we are connecting a cell which is responsible for creating some potential difference across the system. And you know, this is called left hand side gap and this is called right hand side gap. In left hand side gap, suppose if you connect a resistance box which is called a known resistance here. Towards your right, we connect an unknown resistance like this. What is unknown resistance here? A wire of which the resistance is not known to us. In fact, it is that resistance of that wire that is to be determined using a meter bridge. So what you should understand here now, this if I take as a known resistance as R, this we take it as unknown resistance as X. X is to be determined now. That is the very idea while constructing a meter bridge. If you look at carefully, out of 9 terminals, connecting terminals, 8 are already engaged. Only 1 terminal that is left vacant yet. What is that? The middle one. From here, we just connect a wire. That wire is now connected to high resistance that now is connected to a galvanometer and thereby that is connected to a jockey like this. And all of you can understand in this particular circuit, this portion is called secondary circuit. What do you find in secondary circuit officially? A galvanometer will be there. A high resistance of the order of 5 kilo ohm or 10 kilo ohm or 15 kilo ohm that we people used to take up there. What is the purpose of this also every one of you can understand. It can save the galvanometer from the fluctuation of current. Galvanometer is such a sensitive instrument. If at all the input current is more across, that cannot sustain, that cannot withstand. The coil internally may be burnt off. That we don't want to have. We want to save the galvanometer from higher values of currents or from fluctuations of currents whatever they are taking place. Just for that purpose, we people are taking up a high resistance connected across. So what is this high resistance here? It saves the galvanometer from higher values of currents. That's the point. So if you look at this, R is known resistance, X is unknown, I said. Let us say you just keep 1 ohm resistance in the resistance box. That 1 ohm is now known resistance. Then what you have to do? Tapping the wire using the jockey, you find out that point where the deflection in the galvanometer is becoming 0. And you can understand what that time this length of this wire is L1 and the remaining length of this wire you take it as L2. So what is this L1 now to be called? L1 is called balancing length. L1 is called balancing length of the meter bridge. That is the point. If you take L1 as 40 for example, then automatically L2 will be 60 because the total length is 100 centimeter. So you can straight away understand L2 is equal to 100 minus L1. Now apply the condition of Wheatstone bridge to this. P by Q is equal to R by S. So what can we write now? It is R by X is equal to L1 by L2. In other words, you can rewrite this one L1 by 100 minus L1. This is the formula by means of which we can estimate the unknown resistance of the wire using a meter bridge. So every one of you, first of all, to solve this problem number 16, you should know the general concepts related to the meter bridge part of it. Now in this particular problem, we are applying this formula directly. I read out the problem now. A resistance of 2 ohm is connected across one gap of a meter bridge, and an unknown resistance greater than 2 ohm is connected across the other gap. So what you can understand here, towards your left, say for example, there is a resistance of 2 ohm that is connected. So R1 I take this one as 2 ohm, and R2 I take it as X, that is unknown. But you can understand well what is the first length towards left. I take this one as L. Then what will be the second length over here, please? 100 minus L. So according to the given data, in the first half of the problem, 2 ohm is connected in one gap, unknown resistance is connected in the other gap. He has not mentioned what is the balance length. Therefore, I am considering the balancing length towards my left is L, towards my right is 100 minus L. That's what actually he is given there. Then what you should understand, you can write R1 by R2 is equal to L1 by L2 according to that formula I am writing. So what is this R1 by R2 here? This implies 2 by X is equal to L by 100 minus L. This is my first equation. Now what he said in the second half of the problem, what he said, just look at. When these resistances are interchanged, that's the one, the balance point shifts by 20 centimeter. That means this R1 now becomes X. This has come into the left gap. And R2 now becomes 2 ohm. That comes to the right gap. And you should understand what will be L1 now. L1 is shifted. He said very, very clearly, it's increased by 20 centimeter. So I should write this one as L plus 20. Earlier the balance length was L. Now it is becoming 20 centimeter more than the earlier value. That means what you should understand, earlier L and now 20 more means L plus 20. Then what happens to this L2 part? Here it is 20 centimeters increasing means on the other side it decreases by 20 centimeters. So what we can write now? You can write this one 100 minus L minus 20. This value minus 20. So how much is its value now? 80 minus L. You can understand 100 minus 20 becoming 80 minus L. Then how to write that formula again? R1 by R2 is equal to L1 by L2. Same formula. Now you repeat X by 2 is equal to L plus 20 by 80 minus L. This is my first equation and this is my second equation now. Hope all of you might have followed these 2 points. I just have considered R by X is equal to L1 by L2, where X is unknown resistance there. Same formula I have taken twice now. Now what I do while calculating, I just multiply these two. Then what is it you are going to get? Just look at that one. 2 by X into X by 2 is equal to L by 100 minus L into L plus 20 by 80 minus L. I just have taken from 1 and 2. Directly I have multiplied. Then what do you get? X gets cancelled, 2 gets cancelled. So what is left over? You just look at now here. L into L plus 20 will now be equal to 100 minus L into 80 minus L. Come on, just multiply these two. Only mathematical calculation that is left over. I just take up the calculation here. L into L, that now becomes L square. L into 20, it's 20L. 100 into 80, it's 8000. 100 into minus L, that is minus 100L minus 80L minus 180L. Minus L into L plus L square. So L square on both sides, they get cancelled. Now 180L plus 20L, 200L will be 8000. You can cut these two zeros. In fact, this goes 40 times, then you get L as 40 centimeter. But his calculation is not that. He is not asking you to calculate length there. He is asking you what is the value of unknown resistance, neglecting all the corrections. What is the unknown resistance? That is the question he is asking. So substitute this value in the first equation. What will you get now? 2 by x is equal to L by 100 minus L. So L is 40, 100 minus 40 is 60, which is 2 by 3. Then what will be the value of x now? 3 ohm you will be left with. Because 2 getting cancelled, you are left with 3 ohms. 3 ohm is the correct value of unknown resistance there. See the options now. First option 3 ohm, second option 4 ohm, third option 5 ohm, fourth option 6 ohm. So what is the correct option over here now? The very first option, that's going to be correct again. So you can say once again, the answer for this one is again A now. So every one of you, first of all, should have the concept of meter bridge in memory. Meter bridge, if you know, automatically you can even recollect the concepts of Wheatstone bridge also. And in fact, every one of us, we know both Wheatstone bridge and meter bridge are based on Kirchhoff's statements, Kirchhoff's laws only. Only those statements are applied in both the cases of Wheatstone's bridge as well as meter bridge. So what is the correct answer for this particular question is? It is 3 ohm, which is now the unknown resistance. The correct option for that one is the first option. That is problem number 16, what we have in this order. Let us just take up problem number 17. This is also a problem based on meter bridge only. Let me read out the problem. A meter bridge is set up as shown in the figure to determine an unknown resistance X using a standard 10 ohm resistor. The galvanometer shows null point when tapping key is at 52 centimeter mark. The end corrections are 1 centimeter and 2 centimeter respectively for the ends A and B. The determined value of X is how much? That is the concept. Very clearly, he has mentioned us a small circuit. What is that circuit? You just look at. It is a meter bridge circuit only he has given. Like this he has mentioned. This is the base. This is the wire. In between, of course, the end terminals we people are going to have a cell like this. It's given there. Here there is a resistance given. How much he gave? The resistance over here is given as X. The resistance over here, that is given as 10 ohm. And between these two, of course, he has just given us a high resistance like, a galvanometer like, and there is a jockey which of course is taken to tap the wire from A to B. This is the point A given and this one is the point B given. That means in the left gap you have X. In the right gap you have 10 ohm. That is what has been given. The tapping key is at 52 centimeter mark, there is null deflection. So you can understand well, 52 centimeter is this length, that is called L1. Then what will be the remaining length, please? 100 minus 52. That now becomes 48 centimeter. So you all can understand unknown value is X, known value is 10 ohm. In addition to that, one balancing length 52, the remaining length 48. That is what has been given very clearly in the problem. So generally speaking, one resistance is X over here, one resistance is R over here. L1 is given 52 centimeter and L2 is given 48 centimeter. But he has given a wonderful concept at the tail end of this problem. The end corrections are 1 centimeter and 2 centimeter respectively for the ends A and B. That means towards this, the end correction is 1 centimeter. Towards this, the end correction is 2 centimeter. Then what is the determined value of X? So what can we write now? X by R is equal to L1 plus E by L2 plus E. So what can we write now? X is unknown, R is known, that is 10, L1 plus E 53 and L2 plus E 50. So every one of you can straight away understand these two zeros, they get cancelled. Now X is equal to 53 by 5. 10.6 you will be getting in terms of ohm. So look at the options carefully. 10.2 ohm is first option, 10.6 ohm the second option, 10.8 ohm the third option, and 11.1 ohm the fourth option. So which is the correct option here? You can directly understand. It's now 10.6 ohm. That means the value of this is tallied with the second option in the given problem. So the correct answer for this particular question is B. So what is the general difference between the previous problem and the present problem? In previous problem, directly lengths are given, that's all. But in the present problem, what is happening? He has given you the corrected lengths also. End corrections are given. So accordingly, we just have to tackle this particular model. So this is problem number 17, of which the correct answer is B, that is the second option. Let us check problem number 18, the next number. An electric bulb rated for 500 watt at 100 volt is used in a circuit having 200 volt supply. The resistance capital R that must be put in series with the bulb so that the bulb delivers 500 watt is how many ohms? The correct answer for this one is going to be 20 ohm. You all must be knowing well, at JEE level, there used to be fill in the blank type of questions also earlier. Now based on those models, we have picked up this particular question. I repeat once again, an electric bulb rated for 500 watt, yet 100 volt is used in a circuit having 200 volt supply. The resistance R that must be put in series with the bulb so that the bulb delivers 500 watt is how many volts? Let us just take a small circuit here first. There is a small bulb like this, and there is a resistance like this. Both are now connected in series. That has been mentioned in the question itself very clearly. And of course, it is given here 200 volt PD that is connected across. An electric bulb rated 500 watt. So what is the power of this bulb now? 500 watt. Very clearly mentioned. Yet 100 volt, that is the point, is used in the circuit of 200 volt there. So first and foremost, if this is half of 100 volt, observe, very simple concept. If the potential difference across the bulb is 100 volt, out of 200, when it takes 100, how much must be this value? It must be 100 volt again. Hope you might have got this point. This potential difference across the cell, what has been connected across the series circuit, is supposed to be distributed among both the elements. What are the two elements there I am considering? One is the bulb, one is the resistor. If you take the bulb is at 100 volt, he has given in the problem, the other one also should have 100 volt only. Why should the concept be like that? It's very simple. This voltage is supposed to be distributed among these two. When this is at 100, the other one should be at 100. Total put together must be 200 volt. Now, what is the PD across the bulb you take? It is 100 volt. So first you calculate what is the resistance of the filament of the bulb. Resistance, in fact, we can understand one formula here. What is that one? Power is equal to V square by R. Already we have discussed that formula earlier. If you want resistance from this one, it can be written V square by P. We can write that formula over here, which now can be taken V square by P. That is 100 into 100 by 500. You can cut these two zeros. Then what is left? You are left with 20 ohm. In fact, what is this resistance actually? This is the resistance of the bulb. Resistance of the bulb means what? The filament that has been used in that bulb. So resistance of the bulb is given 20 ohm now, and the PD across that one is 100 volt. But you know very well, the PD across the bulb and PD across the resistor both are equal. When will they be equal? When these two resistances are also equal. So what you can understand from here? PD across the bulb is equal to PD across the external resistor. What is the meaning of this one? This implies resistance of the bulb. Resistance of the bulb must be equal to the resistance capital R. What is the reason for this? Since current is constant. How can you say current is constant? Both are connected in series. In series combination, current is the only parameter which remains constant. When current becomes constant, resistance and PD are directly proportional to each other. Therefore, resistance of the bulb and this resistance what is connected in series are supposed to be equal. Therefore, what can I write? R must be equal to resistance of the bulb. What is resistance of the bulb we have calculated? It is already taken as 20 ohm. So, resistance connected in series should have the same resistance as that of the bulb, which I have obtained it as 20 ohm. So, what must be your answer now? It must be 20 ohm only. It is a fill in the blank type of a question, therefore you just have to fill that blank there with what number? 20 ohm here. So I think all of you might have got this particular logic. Both are connected in series. Since both are connected in series, current remains constant, first thing. When current remains constant, potential difference and resistance both are directly proportional to each other. And here the potential difference 100 means here also it should be 100 because the sum must be equal to this. When potential differences are equal, even their resistances are also supposed to be equal. When we know the resistance of the bulb as 20 ohm, automatically the resistance R also should have the same value. That means it should be 20 ohm only. So your answer for this question should be 20 ohm as such. This is problem number 18 for us. Look at the next problem now. That is problem number 19 for us. Find the potential difference between the points A and B and between the points B and C in steady state. That's what has been the question. He has mentioned a wonderful circuit over there. What is that circuit? Let me draw that one first. You have been given few capacitors and few resistances. You will be finding a capacitor connected this way, another capacitor connected this way. And here he said directly one more capacitor that is connected in between these two like this. You can now understand one capacitor is connected here, one more capacitor connected here. And you have been given here one resistance is connected here and one more resistance is connected here. Along with that, a cell is connected this way. And what are the points he has mentioned? First, let me give you the numbers given there. This is 3 microfarad. This also is 3 microfarad. This is 1 microfarad. This also is 1 microfarad. He has given you 2. And one more is given. This also is 1 microfarad. What are the resistances given there? This is 10 ohm resistance. This is 20 ohm resistance. Two resistances he has connected across. And this one is now 100 volt. This is the one. Look at the points what he has mentioned. This point is mentioned as A. This point is mentioned as B. And of course he has given you this point as D, this point as E. Right, and this point as F, this point as G. And this particular point is given as C. Look at just carefully this circuit now. The circuit is just given like this. 3 microfarad, 3 microfarad, 1 microfarad, 1 microfarad and 1 microfarad. This is a 20 ohm, this is a 10 ohm. Applied voltage is 100 volt. Circuit is like this. What is he asking for? He is asking what is the potential difference between these 2 points A and B, and what is the potential difference between these 2 points B and C. That's what he is asking. But all of you directly, while reading the question itself, you can understand. What is that? He has given us a wonderful clue there. He is asking you to calculate the potential difference between A and B and B and C in steady state. So what is the condition for steady state we have to take? In steady state, what you can understand? These 2 are going to be in parallel. These 2 are going to be in parallel. So how to just redraw the same circuit? Now you look at 3 and 3 in parallel means there must be one condenser of 6 microfarad capacity. 1 and 1 in parallel again, that means there will be a capacitor of 2 microfarad capacity. You can now understand the other one is as usual given here as 1 microfarad. What next he has given you, you see there is a resistor 20 ohm here, there is a cell like this, there is another resistor that is of 10 ohm here. This is now negative terminal and this one is positive. This one is of 100 volt. Then what you should understand, this point now can be taken as A, this point can be taken as B, this point can be taken as C. So I have condensed the entire circuit considering the concept of steady state into this form. Now a very simple question it has become. What for? You just look at now. You are finding very clearly 2 capacitors. One is of 6 microfarad, one is of 2 microfarad. Across this one, what is the potential difference? Is question 1. This is across these 2 points, what is the potential difference? That is the second question for us. Between A and B I want, B and C I want. Now just look at carefully this potential difference, I write VAB. This potential difference, I write VBC. These 2 values we just want. One step answer. In fact, you need not put anything on the paper also. By look you can finalize. How come? Just look at. I take these 2, the ratio of these 2 capacitors. C1 is to C2. It is 6 is to 2. That must be 3 is to 1. You can all understand well. 6:2, that is 3:1 is the ratio of their capacities, means they are in series. In series combination, charge remains constant. You can directly understand this logic. When charge remains constant, capacity and potential difference, these two are inversely proportional to each other. So what I can write now? V1 is to V2. V1 is the PD across C1, V2 is the PD across C2. That now must be in the reverse order of capacities. In the reverse order means when this ratio is 3:1, this ratio must be 1:3. And you can understand what is V1 means here. V1 is VAB. What is V2 means? VBC. So VAB is to VBC is equal to 1:3. Now every one of you can understand directly. 1:3 means one part and three parts separately. So put together, how many parts as a whole? 4 parts. Out of 4 parts, 1 part I should give to AB and 3 parts I should give to BC. So what can I write now directly? Therefore, directly VAB is equal to 1 part out of 4 parts. That means 1 out of 4 means what? 1/4 of what? The applied voltage. What is applied voltage over here? It is 100. So 1/4 of 100, that now must be 25 volt. Exactly like that, I just want VBC. 3 parts out of 4 parts I have to go for. 3 out of 4 means what? 3/4 of what? The applied voltage. This now becomes 75 volt for us. So the moment you understand the concept of steady state and the moment you convert this circuit into this form, it is just like that you can finalize what is the PD across these 2 points and what is the PD across these 2 points. So I repeat once again, you need not do all this also. You can take C1 is to C2 is 3:1. Then V1 is to V2 must be 1:3. 1:3 means 1 out of 4 parts and 3 out of 4 parts. 1/4 and 3/4. 1/4 of 100 will be 25, 3/4 of 100 will now be 75. So what is the PD across A and B now? It is 25 volt. What is PD across B and C now? It is 75 volt. So 25 volt and 75 volt, these two are our answers for this problem number 19. PD across A and B is 25 volt and PD across B and C is 75 volt. These two are the correct answers for us. So 25 and 75 volt, you people have to remember as the correct answer for this question number 19. Let us take the next number, problem number 20. 2 resistors 400 ohm and 800 ohm are connected in series with a 6 volt battery. It is desired to measure the current in the circuit. An ammeter of 10 ohm resistance is used for this purpose. What will be the reading in the ammeter? Similarly, if a voltmeter of 1000 ohm resistance is used to measure the potential difference across the 400 ohm resistor, what will be the reading in the voltmeter? That is actually the concept. So what you should understand first of all is the first circuit I am talking about. There are 2 resistances connected in series this way. One is 400 ohm, one is 800 ohm. Both are connected across a cell of 6 volt. And we know well, an ammeter is connected across this, he said. Ammeter of 10 ohm resistance, he said. So what you should understand, what is the total current across the system is the question. So simply you take what is the potential difference applied. What is the effective resistance of the system? What will be the effective resistance? All are connected in series. So 1206, right, ohm you will get. That is 1200, 1210. Look at this one carefully. 400, 800, 1210 ohm. Now you take these two. What is the current across the system? I is equal to V by R. 6 by 1210. Nearly I take this one. Nearly. Remember this point carefully. 6 by 1200, like if I take, it becomes 1 by 200. 1 by 200 is nothing other than 1 by 2 being 0.5. You can directly write 5 milliampere of current. So it is a nearby answer I am taking up here. It is around 5 milliampere. That is the total current that is passing through the system. So first part of this question, what he is asking you is, what is the reading of the ammeter? The reading of the ammeter will now be simply 5 milliampere. That is one value you have to remember. Then what he did in the second part of the question, try to understand that one. Similarly, if a voltmeter of 1000 ohm resistance is used to measure the potential difference across the 400 ohm resistor. So what we should understand, same circuit I draw once again. Look at these two are the resistances. This one is the cell. This one is the ammeter. This is of 6 volt. This one is of 400 ohm. This is of 800 ohm. Till that extent common. But all should understand straight away, whenever we connect an ammeter in any circuit, it should be connected in series always. Whenever we connect a voltmeter in any circuit, it should be connected in parallel across those points where the potential difference is to be measured. So what should I understand now? This must be the voltmeter. Why should I connect across 400? He is giving you in the problem very clearly, he just wants to calculate the potential difference across 400 ohm resistor. So what we can understand here, this is of 1000 ohm. This is as usual of 10 ohm. Now first you estimate what is the effective resistance of this system. What is effective resistance over here, please? It is 1000 into 400 divided by 1000 plus 400. You now can write this one directly as 2000 by 7 ohm. That is the resistance over here. So if you take this particular part of it, its resistance is 2000 by 7 ohm. Now for example, if you take this one as 800, the other one what has been given. So tell what is R1 is to R2 first. This is 2000 by 7 is to, this is 800. What is happening here? I am not considering this value because that is a meager value, 10 ohm. Earlier also, by neglecting that only, we people have got nearly 5 milliampere. So what you should understand here, this now becomes directly, you can cut these zeros and other things, like it will now be 2 times 400, right? Here 5 times. So 5:14 you will be getting the ratio. Resistance ratio 5:14 means even potential difference ratio also will be the same, 5:14 only. Now I want, what is V1? Look at carefully. 5:14 means for the first one 5 parts and for the second one 14 parts. We have to divide the potential that way. One for 5 parts, so for the second one 14 parts. Total put together 19 parts. So what should I write now? Therefore, V1 is equal to 5/19 of 6. So it is 30/19. Roughly, if I estimate this one to be 20, like, you will be getting nearly 1.5 volt. So what will be the corresponding voltage across this one now? It's 1.5 volt. What is the current that is across the system now? Around 5 milliampere. So what will be the correct answer over here? Current is going to be 5 milliampere nearly, and potential difference across 400 ohm, that is around 1.5 volt. So these two are the correct options one should consider for this problem as such. But only thing you should understand from this model is, any time in any circuit, ammeter is always to be connected in series. Voltmeter always should be connected in parallel. Parallel across what? Across that particular appliance, across which we just want to calculate the potential difference. For example, in this problem, he just wants to calculate the potential difference across 400 ohm. Therefore, we should connect that voltmeter across this. Suppose if he wants us to calculate the potential difference across 800 ohm, then you have to connect this one across 800 ohm there. So this is actually the method what one has to follow. So voltmeter should be connected in parallel and ammeter should be connected in series. That is the basic concept one need to understand to solve these model questions like. So this is problem number 20.